My name is Sumit, and I'm going to talk to you about BigSense and using Scala to build a framework for measuring sensor networks. So basically my presentation is going to cover, I'm going to talk about this project that we had called the Green Learning Station in combination with the Civic Garden Center. That's how we got pulled onto this project. Going to talk about Java web frameworks. This is stuff that we're probably all familiar with, so it'll be a really quick refresher. Then we're going to talk about creating a custom framework in Scala, and we're going to talk about BigSense. So BigSense started off in Cincinnati, Ohio. I was out of work. I was between jobs, and I was at this birthday party, and this person named Andrew Rettig said that we're trying to do this thing. He was a geography PhD student, and he was working on using embedded Linux systems to gather sensor data. And we're talking about using BeagleBones, and then eventually went to just embedded routers, just regular home routers that we reflash with OpenWRT. And we're using that to gather things like weather, rainfall, temperature, humidity, and so forth. So the original purpose, so this is a combined sewer overflow. Let me see if this video will play. All right, so in the city of Cincinnati, and so that's coming out through these speakers, it's pretty loud. In the city of Cincinnati, we have a combined sewer overflow. So all the stormwater and all your sewage goes into the same pipes. And because of that, and it's a good idea in theory, because now you're putting all of your stormwater into sewage treatment. And there's a lot of pollution in stormwater. There's salt, there's the stuff off the bottom of your cars, there's everything that's coming off the street, tons of pollution, so you can treat it. But the trouble is when you have a heavy rain event, and in Cincinnati we got very heavy rain events, this would overflow. And they would overflow into these levees, and then eventually these levees would overflow into the river. The idea is that if you have a large rain event, you are diluting the water, but you are diluting raw sewage. So that is quite literally a ton of shit being dumped out into this reservoir. There's better, here's the other side of that same one. So yeah, so this was taken by Andrew and Quinn. I think actually this was taken by Quinn, and they just went out to this overflow. So you can see the other side of this levee. And this is during a heavy storm event. It got so bad in Cincinnati, so Cincinnati systems were not designed very well, and they actually had backup into people's homes. It got so bad that the city was sued, and they lost the lawsuit. I don't know why they would try to fight it. But if you live in Cincinnati and you have sewage backing up into your homes, they are required to clean it up if you live within the city. They even had to mail out refrigerator magnets that told us that they were required to clean it up for free. So this is the Green Learning Station. So the city needed to deal with this. And ripping out tons of sewage systems that's already laid down is not going to be practical, especially for a city that's already running out of money. So the Green Learning Station was this idea to test permeable pavers. So one thing you can do is just reduce the amount of stormwater that gets into these systems, that gets into your drains, into your sewer systems. So all these companies offer permeable pavers, things like cobblestone, things like permeable asphalt, and all of them say they're the best. How do you know if they're the best? You somehow have to be able to measure rainwater runoff. Stormwater runoff is the largest non-point source of pollution. And what does that mean? Non-point source of pollution in geography terms, in environmental sciences, it's basically an NP-hard problem. It's very, very difficult to do. It's pretty much impractical except for small areas. So the Green Learning Station has several different pavement types. There's 6 pavement types total. We have permeable asphalt, white permeable concrete. The middle one is concrete, so that's a non-permeable surface. That's our control. And 3 types of permeable cobblestone. At the ends of each one of these surfaces is a sewer grate, and the sewer grate goes down, I think about 1.5 meters. And so you can crawl down into sewer grates, and they're fake sewer grates. They don't go anywhere. They fill up, and then we pump all the water out, and we measure the water that we are pumping out. So here's a top-down view. So this was originally a parking lot for the Civic Garden Center. It used to be a gas station, and they donated to the city for this project that they were doing in combination with them. The Civic Garden Center is a nonprofit, so they do a lot of sustainability. They have school trips. They teach kids about gardening. They teach people about sustainability and green roofs, and have bonsai classes and all the things that most community nonprofits do. And so they had this petrol station that they weren't using for quite a while, and they just used it as a parking lot. And so here they converted this car park into this learning station. And so each one of these segments is actually separated out, and we'll see in a second how that's all separated out. Here's a side view. So you can see they have a green roof, they have a water collection barrel, they have lots of other projects going on at the same time. This service here is actually not in our papers. It's at the wrong angle, so we decided not to use it. So this is a map of the Green Learning Station in its relationship to Cincinnati. So there's the Green Learning Station, there's the park around it. This was done in ArcGIS, which is a major industrial graphical information software. And here are all of our sensors. So we gathered all of our sensor data. For this particular project, we actually measured where each sensor was placed in the ground to get some high precision. Later on, we just kind of wanted to group sensors together locality by the relays they're attached to. But for this specific project, we got every one of the sensors. So these are all our temperature sensors and our water sensor for all the different pavement types, including our rain meter on the roof. And then we had some in the back that we didn't actually get to implement. I believe those were also for rainwater runoff. So the methodology. So each of these pavement zones was about 8 by 14 meters. And they're all completely separated out on the sides. They're completely lined off. They had concrete barriers between all of them. Each zone was about 0.9 meters deep, about 3 feet. And so the bottom consisted of a plastic liner. And on top of that, they had a concrete bed. Above the concrete bed, you have a 1/3 of a meter cobbleside rock. And on top of that, a 1/3 of a meter of gravel. So this is how most car parks are laid out. If you go to a modern shopping center that's just been built, underneath it, if they've tried to do some type of green drainage system, it will most likely be set up this way with pea gravel, impermeable gravel, and then hard concrete at the bottom. And the engineer who was working on this, who was the contractor constructing the site, was really interested in the data because he wanted to know how much all this stuff actually worked at reducing stormwater runoff. So we looked at embedded boards. At the time, Beagle boards were still going around $200, I think. If people aren't familiar with them, Beagle boards are single board Linux systems that have a USB port on them, GPIO pins, kind of like the Raspberry Pi, but more with more basic input-output, more GPIO pins on them. At the time, we could get routers really cheap. This is a Linksys E2100L, so it's just a wireless N router. Runs OpenWRT stock on it. And so we just downloaded OpenWRT. I think for this one, we had to change one line of code in a .h file, but it compiled fine, flashed on there. These have a USB port, so we could attach our sensors using a one-wire dongle. And one wire is a protocol that puts all of the data and power over one wire. So you have one wire going in and out, so really 2 wires, your power and return. And it has capacitors that hold power, so it multiplexes the power and data. And you can have several of these on one circuit. We actually talked to a Chinese engineer. So in China, they use these sensors in grain silos. And the government contracted out this one company to put them all in grain silos. And they had these strands that had over 1,000 sensors on them going straight down through the grain silos. They're very slow because they're multiplexing power and data. It takes time to get all the data out. I think for theirs, it took over 1 hour to 3 hours to get all the data back, depending on the size of the grain silo. For our purposes, where we just had 3 to 5 sensors, it only took about 2 seconds. It's still slower than an I2C bus, slower than an I2C bus or other sensor types, but it is very low power consumption, and we have the advantage of it just being over one circuit wire. As we use for the Green Learning Station, yeah. So the Green Learning Station, these aren't Linksys. We use another router called a Netis router. They had slightly higher capacity on them. The Linksys routers have about 8 megs of storage. These had about 16, and this was important because the client is actually written in Python. So there's a small Python interpreter in there, Python Mini, and we have a program called LtSense, which reads all the sensor data using an open source one-wire driver called OWFS, one-wire file system. It can create a file system that represents the one-wire sensors using the Linux userland file system, or you can just read the data directly using their API. And so we have our sensor dongles, and we have our USB sticks that we just use to store data. If we lose connectivity to the server, these things just store the data. So it keeps a buffer. It can keep the buffer in memory, in which case if you turn off the power, you lose it. Or it can keep the buffer on a file, which is what we do. We put it on a SQLite file on the stick so that once connectivity is restored, it will then just send all of those in a controlled fashion back to the server. Here are GPS coordinates for all of our sensors. So we measured these out earlier. The GPS unit that we used, I think it's called a Tremble GPS. It's very precise. It requires a base station. I think it costs $3 to $4 grand. There's actually a backpack that goes with it. One of the professors at the University of Cincinnati had one of these, was nice enough to lend it out to us. And Quinn went down and actually took readings on all these sensors. I think they're accurate up to 3 centimeters. And our base station was the airport at Cincinnati. So we used that in conjunction with GPS satellites to get all this data. This data is stored in spatial databases. So BigSense supports MySQL, Postgres, and Microsoft SQL. And it's kind of interesting because the spatial part looks about similar. It looks very similar to what we just saw earlier. The point methodology and the queries are pretty standard throughout most geospatial databases. So this is our data flow. So we already talked about these sensors. We talked about these relays running OpenWRT, or in the future, we're actually going to be running Debian embedded. And those go to a web server, and then we can take the information that's put in our web server, aggregate it out, put it into data formats, and then put it into web applications. So for this particular presentation, we're going to be talking about the right side of this graph, and not the left side of this graph. If you want to look at the left side, you should come to a Python meetup. So the technology stack behind this, we have BigSense, which is a web service written in Scala, using embedded Tomcat and Jetty, which is kind of neat. I'll get into that in a minute. The client side is LtSense. It's written in Python. Supports multiple formats. Right now, we're just using a proprietary XML format to get data back and forth, but we want to implement using WaterML and several other formats. Using one-wire sensors. There's also a component called vSense. So if you're sitting at home, you're interested in this project, you're like, wow, this is a big project, I don't know how to set this up. You can clone vSense. It's a repository with a bunch of Ruby scripts. It will just set up a bunch of Vagrant VMs, set up everything, and build everything for you. And you'll have a fully working BigSense and LtSense environment. The LtSense environment gives out fake sensor data that it just generates randomly. And this helps get developers on board quickly for people who want to volunteer on the BigSense project. And this was originally packaged for OpenWRT, but now we have packages that are automatically built in our continual integration system for Ubuntu, Debian 7 and 8, OpenSUSE, and CentOS 7. So next we're going to examine web service frameworks. So all of us here, most of us here who are Java devs have used, I'm hoping we've used some type of web service framework. We're going to go over web service framework, look at a servlet, and look at how we construct a BigSense on top of the servlet layer. So web service frameworks, I'm sure most of us use these, struts, REST-easy, JSF. So REST-easy and Access, these are both web service frameworks. Access, of course, is for SOAP. REST-easy is kind of just a bunch of annotations to make REST a little bit easier. JSF is some failed attempt at web forms in Java. Struts and Play are MVC frameworks. Now, all of these frameworks, except for Play 2, all run on the servlet container. So they can run on top of Tomcat, on JBoss, on IBM WebSphere if you hate yourself. And the Play 2 uses its own engine behind it, and they finally rip out and get away from the servlet layer. You can deploy Play 2 applications on a servlet container, but it's a wrapper that binds that all together. So let's just take an example of REST-easy. So I once had a job where I was writing REST-easy services. And so in my REST-easy service, we have annotations that define what each function does. So I want things that are posts that have this particular path to go to this function. And then we map all of our input parameters. In this particular project, I created a service request object that I just dumped everything into, and then I invoked that service. And so my service request object had pieces for post, get, delete, and so forth. And here we see the delete. We have delete, the path to it. So REST-easy maps that URL and that pattern onto this function. And I'm putting it into the same type of request service object. And we see the same thing with get request. They're just slightly different. I put them into the same request service object. When I started working on BigSense, I'm like, in all these cases, I'm unwrapping everything and kind of rewrapping things. Why do we have different annotations for get, post, delete, when really, if you have an action, within the action, you kind of want to define what each piece does? And where that comes from, if anyone has actually worked with the servlet API, if you're working with the servlet API directly, you have do delete, do get, do head, do post, do put. And so all of our web service frameworks, with the exception of Play 2, all have this at the core. So underneath JSF, underneath struts, they have some type of base layer that interacts with this. And all of these, OK, so this is just a simple do-get servlet. This is something I did back in Computer Science 201 about 10 years ago. And one of our projects was to write a balanced tree. And I decided to do it as a servlet because, hey, I should just learn servlets. And that was a horrible idea. Tomcat 3 crashed a lot back then. And you had to reboot the whole thing to reload applications. But it's pretty simple. You have a request and a response. You get the output stream, and you send things to the output stream. Here I'm sending straight HTML. all of these implement this service. So within that service layer, you do get, do post. They're all called by the service function. And this actually dispatches everything to the individual functions that we saw earlier. We also see this service function that doesn't have, so these are HTTP servlet requests and response. And then we also have the service function that doesn't have an HTTP servlet request or response. The original idea behind servlets was that they wanted to use these for a bunch of things. You should be able to have SMPT servlets and SSH servlets, and you should be able to implement all kinds of services in Java. This never really happened. There were a couple early mail servers and things, but none of them really grew. And the only thing we really saw come out of this in major scale use today is HTTP servlets. And I want to see, so they tell you not to override these functions directly, that just override the sub-functions that do get, do post. I want to see what these functions actually did. The service method, it does some check for last modified. It has some caching response in there. But other than that, if we just scroll down through the code, all it does is directly call all the other functions we saw earlier, do post, do get, depending on the method that you used. So when I was building my framework, I decided to toss that on its end. I overrode the service method directly and used that to dispatch everything. So I'm going to talk about what I used to build my own framework. And I did this in Scala. It has several components. These components are probably pretty familiar to any of you who've worked in MVC. We've got actions, validators, formats, security, converters, and then we have this master servlet that bootstraps everything together. So an action. So an action is kind of what we saw earlier with that service request object that I had. I just put everything in here. So the method, the arguments, the parameters that come in, the models which are populated in the bootstrapping process. If there's data, it will extract that data and turn it into models, in our case XML data or JSON data. Then there's a format which is used for output. So if something is being returned, it's going to be in a specific format. The signature is used for security, which I'll go into in a second. And then we have a nice string formatter just for debugging. An example of an action. Sorry, so here's an example of so this is the response. So we have an action, we have a response. So we have a basic response type, class response, I have our status, content type, new locations if they're new headers. So we have three basic response types: binary, string, and a view. For the view, I'm just using twirl templates that are standard in Play 2. Twirl is the templating language used in Play 2. It's been extracted into its own project, and you can just implement it in your own project as so. And then we have some defaults that are pretty sane. So the action trait. So every one of our actions implements the action trait. So those of you who are not familiar with Scala, a trait is similar to an interface, but you can have methods in it. So it's similar to an interface and an abstract class. You can also use it as mixins, so you have this sort of multiple inheritance. Traits are very powerful. If you start, I'm not going to go into a huge detail on traits, but if you go through some of the Java boot camps for Scala devs or Scala boot camps for Java devs, you can get into these, and they're really interesting. In Scala, you actually have properties. So these are actual properties that you can assign directly, which we still don't have in Java 8 for some reason. If you need to implement things, so we are using some Spring dependency injection in here. So if you're using things that still rely on getters and setters, this beam property annotation generates the getters and setters in the compiled bytecode, kind of like Lombok. And then we have our run action that takes in a request and gives a response. So in Scala, these are kind of reversed from where you see it in Java. You have the variable, the type, and then a colon and the response. So within our actions, this is a query action. So we want to be able to query sensors. In this case, we're checking the method. If it's a get, then we check the second parameter if it's latest. And then we call our model and then send back our Spring response. We render our models from the database handler, sends it back to us up through the loop. And here we can see timestamp range, date range. There's also a case for the post. And later on, we don't have delete implemented, but that could be down there as well. And notice there's no validation in here. We'll get to that later. There used to be validation here, but that's been pulled out. So we have validators. So the validator comes in before you get to the action, and we basically just copy these HTTP serverless response, bad request, not implemented, not allowed. We have some basic functions for checking things like dates, longs, and integers. And then we just have the validate request function. And then we have validators that implement those functions. So here we see the same method to check when we're doing a query for the latest to make sure that we just have valid input, valid numbers, and so forth. And here's where we throw our errors. So we have several different data formats. so on the output, we have tab delimited, comma separated. We have our own proprietary sense XML, which is what we use to pull data in. We can also output data with that. For the tab delimited, comma separated, they're only output formats. You can't actually write to the database in it. And to get a nice pretty print, you also have sortable HTML tables. So our data format trait, so we have a trait again. It can render models or it can load models. Of course, not all the formats implement both of these. Many of them don't. Many of them only implement one. So we have a flat file format trait for both the comma separated and tab delimited. And so in our render files method, so this is kind of nice because we have this, for comma separated and tab delimited, they're pretty much the same thing. The only thing that changes is just your delimiter. So we have all of our logic to build all of our rows down here in the render models function. And they call these render row and render header functions. And then in our implementations, it's really simple. All we have to do is do a row reduce on our output set, and it compresses everything back. So here we do row, reduce left, takes in our A, B values, and then generates our list. So here we have tab delimited and comma separated as well. So some of the Scala notation can seem kind of strange, but it's really powerful once you get your head around it, because you can reduce things very quickly, and you can create things in very small amounts of code. And you can still put it in such a format, if you do it right, where it's still readable and clear as to what's going on most of the time. Data formats. So originally when we pull data in to BigSense, it's being transmitted from LtSense in our own XML format. One of the things you can do in Scala, and this was an early design decision that some people have been very critical of for a good reason, is Scala does have XML support built in directly into the language. So here we can see we're doing straight XPath queries in language syntax, for better or for worse. In the Java world, you can trade out your XML parser. You can use JDOM or DOM or SAX, depending on if you want streaming or if you want. You can deal with all the trade-offs of having a slow versus fast parser, depending on what you want to do. Scala has a built-in one. You don't have to use it. I was using it because this was my first Scala project. I saw this. I'm like, this is kind of neat. There are a lot of problems with this. The biggest problems are in IDEs. Syntax highlighting this is a pain, and creating parsers that deal with this, because each one of these, whenever you do one of these, expands out to a little object. And that gets into a problem.
Sorry to interrupt. It was hated so much that it's now gone. It's now a separate module that you can bring in if you want to, but I think the module is unmaintained, so the latest Scala doesn't have it.
I believe so, yeah. I think in my project I actually have to import it in directly as dependency. But here it is in use right there. And then we also use this to output HTML or output XML. So here you can see XML tags. And then each one of those XML tags actually creates an object. All this unwraps. So we have all these closures that unwrap back up so that we can actually take out our data model, extract everything, and then loop everything back up and create these XML objects. So what's the sense XML actually look like? This is what it looks like. We have sense data. We have a package. You can have multiple packages per transmission. So the package itself contains a timestamp. So a package represents a moment in time, and it represents what all these sensors represent in that moment in time. So here we have a temperature sensor that's transmitting units in Celsius. And so this temperature sensor has a unique ID and it's saying it's 34 degrees at this particular point. We had these water sensors. So a water sensor, when you talk about a rain gauge, there's several different types of rain gauges, but one kind is a tipping bucket. So we had our rain gauges were 1/100th of an inch, and every time they filled up, they'd tip over. And that's how we knew how much rain had gone. The sensors in these huge sewer pipes that were pumping out water. So the way that those worked is after they were filled, after a rain event, when they hit the top, a float would trigger, just kind of like the float on the back of your toilet, except when it clicked, it would pump all the water out. And we would measure that. We had a rotating disk, and every time it rotated, so many liters of water was removed. And so we had this number, and this number represented the total volume of water pumped out from the system since we started it. And that's not really a useful number. In November, if you're saying that we had 390 gigaliters of water pumped out of this system since March 1st, 2012, that's not very, it's kind of like a Unix timestamp. So we needed some way, so we broke that sensor into two different things. We have volume, and then we had a flow rate. So volume is exactly what I said. That's the amount of water pumped out since we started the project. And all of these sensors, especially the ones in the sewer grates, had little batteries on them, so they would never reset, even if we lost power. The flow rate takes the amount of volume over a sample rate. So our sample rate was 5 minutes. So we take the amount of water we've pumped out over those 5 minutes and gives us a flow rate. For the rain gauges, this made sense. We'd actually get a flow of rainfall because we monitored those had a sample rate of 1 per minute. For the sewage grates, the flow rate doesn't make as much sense. So we really, because they're only activating after these things have filled up. So we needed to really get volume, and we needed to aggregate that over a large amount of time. So that's what we're going to get to next. We also had security. So we need to make sure that this data is actually coming from where it says it's coming from. So there's a public key that's put on each one of the routers, and all of the data is signed with that key, and it's verified when it comes back to the server with the private key that we have on the server. There's a security trait that has a security filter, and so that gets to the data even before it gets turned into a model. So right at the beginning of where the request comes in, there's a disabled security manager, which just returns true, obviously. And then we have a real security manager that will chop off everything after the second new line, see if there's a signature there, and then verify that signature with what we have in the database. And if it matches, write it to database. Otherwise, throw an error. I believe it was 400, or I believe it was not authorized. And so this is what it looks like. So we have our sensor data, we have our 2 new lines, and then we have a signature. And really, this is all one line. I've just kind of split it out so we can see it. And wait, was there anything? Yeah. So next we have conversions. So we have a conversion trait. So within the database, when things are coming back out, these are all REST interfaces. So you can have a question mark and have units equal standard or units equal metric. And if you're moving the data back and forth, we have this conversion trait that deals with these conversions. We really only have 2 conversions, one for units and one for time zones. And so here we have our unit conversion. So we just statically put in changing things from Celsius to Fahrenheit, millimeters to inches, and so forth. The site was made in the US, and for some reason everything is in imperial units, but everything by default in the database is in UTC and in metric. And then we have the same thing for time zones. This was before JOTA time, so we have some really fun fandangling to get time zones to work correctly, which will hopefully be ripped out soon. And then we had a lot of Spring glue. So this was back when I was getting involved in Scala. I didn't learn about dependency injection in the Scala world at that time. And so there's still a lot of Spring components in there. Here are all the actions that we talk about. So here are all of our actions. They each take in all of these validators. And there's a base action that takes in our database handler. So all of these get that database handler. We have all our validators that are all named here that are attached to those actions. We have all our formats. And we have logging. So I'm using aspect-oriented programming to capture logging. So we just have logging wrapped around. So there's no real logging code in any of the classes except for the database classes because we need some more fine grain there. But for everything else, when any one of these objects is grabbed out of Spring through dependency injection, it wraps it in a proxy object, and then we can grab trace logging using this. I'm hoping to, over the next course of the month, rip out Spring and just replace it with code so that we have all the dependency injection just in one file in code. In Scala, you can also use things like the cake pattern, but those get really complicated, and it's just easier to just write it out in code and compile it as such. And that way you have compile time checking of everything. And logging we're hoping to replace with AspectJ. And so all of this has to be run as a web application. So originally, this was all put into a WAR file, and this WAR file was deployed to a Tomcat server. And I know a lot of us probably use projects that come bundled with Tomcat, things like Alfresco, things like all the Atlassian products. They come, Adobe CQ, they come bundled with their own Tomcat server and everything within the bundle. And I always found this kind of strange because I'm like, shouldn't you just be able to, there are only a few configuration files that you ever really change. You never change any of that stuff. You never set up SSL within your Tomcat container. If you need SSL, you usually put a proxy on front of it, HA proxy or Nginx or whatever, to handle the offloading, usually on the same server. And so couldn't you just embed Tomcat? You can embed Jetty, and so that's what I started out with, using Jetty as an embedded container. And so here we have just a Jetty server that I created, and we start that. And I want to see if I could do the same thing with Tomcat as well. And so that's what I'm trying to do here. So I started off with this trait, and the only thing that's really configurable in a project, the only thing I really care about, the only thing I've ever really configured in a Tomcat container is the port, and maybe database information if data sources are in the Tomcat container. So we set the port, and then we have the stop and start server in this base server trait. and then we implement this straight. So Jetty is pretty straightforward. Just go to the Jetty documentation, copy and paste, and change it all from Java code to Scala code, and it's pretty straightforward. You set your connectors, you set your servlet engine, you set your web root. So I'm setting everything in /* to go to my master servlet, which is the bootstrapping servlet. The master servlet implements service, runs the validator, runs the action, runs security, does all that stuff, and basically glues everything together. In Jetty, you can set a context path for all your static content. So all of our static content is just placed into a jar file, it's compiled in, and anything that needs to be pulled from static content gets pulled from there. We set up our handlers, and this just works. For Tomcat, this was a bit more confusing. There's not a lot of documentation on it. I was ripping through some things. You have to set up some temporary directory or set up a temp dir. But here we're doing basically the same thing. Once I got my head around the Tomcat API, we import it, we add our context, we set up, we add a servlet, which is our new master servlet, create our CTX mapping. Tomcat, as far as I could tell, couldn't do static content delivery out of a jar file. I couldn't seem to find a way to do that. You can do it from a file path. And in the Tomcat world, it blows up your WAR application before it starts serving your content. So that kind of makes sense. So within this context, I had to create a static content servlet and map all the static content to that. And it's a really basic servlet. All it does when you request something that's static content, a JPEG file, a PNG, whatever, it just tries to associate the right MIME type, find it in the jar file, and send it back. So that's a lot of code. It's a lot of information in your head. So we're not going to go, there's plenty of other code. There's the bootstrapping servlet. It's pretty basic. It glues all these things together. There's configuration, basically all the configurations in one file in etc BigSense, and we read that in and configure all of our components with that. There are tons of database components. I'm not using a DBO with BigSense. With BigSense, I have individual command files. So there's a MySQL, Postgres, and Microsoft command file. I just found that easier when trying to support multiple databases, especially when using spatial query than trying to use Hibernate or some type of other database abstraction language. There's also the SBT native packager, which is a plugin for SBT. This was originally all done in Ant, and I've transitioned to SBT, which is really good. Even if you guys are in companies where you're using mostly Maven, if you're not using a lot of Maven plugins, especially if you're not using any Maven plugins, I would highly recommend trying to switch to SBT. If you have existing projects that don't use any plugins, just try putting SBT in there. It will usually just build right away. You have to translate all your dependencies. But it's much, much cleaner, runs much faster, and it works fine with Java projects as well as with Scala projects. We use the SBT native packager to create all of our Debian and RPM files and place those all in our repositories. And so we support Debian files for System 5 and Upstart, so that's for Debian 7. For Debian 8, we also have systemd Debian files as well. There are 3 different repository trees you can grab from. For RPMs, we only support systemd because pretty much CentOS 7, OpenSUSE since 11.4 have all been on systemd since then, for better or for worse. Configuration file, which I mentioned, pretty straightforward. We just have all of our database information, usernames, passwords, the security manager, port, whether the server is going to be Tomcat or Jetty. And then, so notice we have a DBO user and a DB user. Why do we have both? The DBO user is just used to initialize the schema. So when the service comes up, creates all the schema, and then it downgrades itself to just DB permission. So that's another just added layer of security to help, just so that the regular user that's running doesn't have DBO privileges. Once you set up this file, you can just run BigSense --ddl, and it will create the initial database file or the initial SQL file to create your database based off this information. So this initial SQL, or whatever you pipe it out to at this point, has all the create commands for either Postgres, MySQL, or Microsoft SQL with all these roles or users, whatever is relevant to your particular database dialect. And you can run that as an admin user for your database, and you're already ready to go. There's a web service API, of course, because this is a REST web service. And on BigSense.io, you can see this whole API. Here are many of our requests. So most of these are query-based requests. You can query the sensors, the relays, query based on timestamp, date ranges. We can also have aggregation. So this is the important part. When we're talking about water volume, we want to know water volume over a period of time. With the aggregate functions, so here we have some volume, you take the sum of all the volumes over a date range. So from like January 1st, 2012 to January 20th, 2012, over an interval of time in minutes. And that gives us a nice subdivision so we can see our averages. So here's an example query. So here I'm querying our green station data, gls.bigsense.io. I'm aggregating the average temperatures over a date range. In this case, March 1st to March 3rd, 2012, over 60 minutes. So it aggregates over an hour. So as we can see here, we have the averages for those sensors within that hour time period. And then here we have the next hour time period, and this continues on. Here's a similar query. So here we have, we're taking the sum volumes over a date range, in this case May 1st to May 10th, over 1,440 minutes. That's 24 hours. So this is how much, these are the sensor readings for one day. Where are my dates? Yeah, so that's one day. Here's a second day, and this goes on. So we know that within this one 24-hour period from this pavement type, from asphalt number 1, 695 gallons of water were pumped out. And some of these got quite huge, over 1,100 gallons, 2,500 gallons. So some of these are quite large. Here we have 20,000 gallons, and you're like, that's a lot of water. The next time there's a huge rain event, next time there's a huge rainstorm, take a look down at sewer grates. You'll be amazed at just the amount of stormwater that goes into these grates. It's quite amazing. Even if it's not a major storm event, just go out after it's been raining for a while, and you'll just notice that it is quite a lot of water that gets pushed directly into our sewer grates. All right, so that's BigSense. That's what you can do with it. In the future, we want to support a lot more sensor types. I'm still working with Andrew back in Cincinnati. Right now I'm on the road, so I'm working remotely with him, and he's got a bunch of sensors hooked up to Beagle boards. So for the future, we're going to be using Ubuntu-based Beagle boards, building packages for them, supporting more I2C sensors, one-wire sensors. We're going to do a lot more database optimizations because it's a little bit slow doing some of these aggregations right now. We're working on indexes. We also want to add some asynchronous operations to the queries, because right now we're waiting on the database to finish and then spitting everything out back to the user. Where in the future we want to have the database queries just spin off and already begin spitting out responses as they're coming back in from the database. There is some support for this in the Servlet 3.0 API, but we might look at going the more netty route as Play2 does. Not sure at this point. We're still examining that. Adding more GPS and geospatial APIs so that we can query sensors based on a point and a radius or on a polygon, similar to what we saw earlier. So we can get all the sensors within a certain range based on a certain accuracy. And working on things so you can self-register sensors. So a relay can announce itself, register itself, get its own public key, and so forth. So the source code for all this is up on GitHub under the BigSense organization. So we have BigSense, we have the BigSense tester, which is a whole set of Python test suites that does integration tests against BigSense. LtSense, which is the client written in Python. vSense, which is the virtual environment that brings all the other things up. And this presentation is written in Reveal.js, and it's a bunch of small files that are just pulled together into this HTML file, which you can see here, and there's several presentations on there for Scala talks and Python talks and so forth. If you're interested in contributing, because you have tons of spare time to spend on all these open source projects, you probably don't. But if you do, we do need a lot of help testing vSense. vSense, Andrew Rettig, the person I worked with, has actually gotten his PhD, and he's going to be teaching a class using BigSense, LtSense coming up in the Northern Hemisphere fall of 2015. So we're going to be using vSense with our students and getting students involved in this and trying to set up sensors community gardens. So if you're interested, we need a lot of help testing vSense. If you already have Vagrant and Ansible, a pretty recent version on your machine, it should be pretty easy. The install instructions are pretty straightforward. If you find mistakes, put out issues, help us out. We're working on BeagleBone back support. If you have a Raspberry Pi that's been sitting around forever and you've done nothing with it, get on our mailing list, because we do need help getting Raspberry Pi support, getting the Python stuff working with Raspberry Pi, so we can start using the GPIO pins and analog to digital converters on the Raspberry Pis. If you're familiar with I2C, we're also looking for help on that. Funding, we're looking for grants, sponsorships, fellowships. If your companies are really involved in this, or if you know of fellowships or know of professors who are interested in this, please let us know. Either talk to me or find me on the mailing list. And we have a mailing list on Google Group that you can subscribe to. It's not very busy, and it's a great place just to talk to other people who are currently working on this. Also, if you feel like donating us some Bitcoin, here's our QR code. I don't see anyone getting their phones out. All right, that was a good try. All right, so any questions?
Why did you write your own web framework? Why did you do something?
Okay, so the question was, why did I write my own web framework? Like I said, I did this while I was out of work. I wanted to learn Scala. There were some Scala frameworks at the time. I was just kind of learning everything from the base up. I had a lot of time on my hands, and I was familiar with the servlet layer. I'm not exactly sure why. It just kind of started evolving out of that. And I saw, I was looking at just how to handle requests and looking how to do things in the Scala way. And it just kind of started to make sense to kind of blow it out. And once I started writing it, it was just really easy to write. And a lot of times I'd struggled with other web service frameworks because I was trying to figure out what they do. And with this, I saw the whole stack all the way down. So it became easier to figure out, to get it to do really what I wanted to do from the ground up. Cool. Anyone else?
So how often are the people at Cincinnati, are they still using BigSense and LtSense and LtSense?
That was running for a while. It was running for over a year, and we have the collective sensor data from that year. There's a startup that formed out of it that kind of fell apart, and I think they tried moving to a different web service framework, but eventually the site, it actually hasn't been in use. Andrew checked out the site recently, and it hadn't been used for a while. One of the big problems, we were using OneWire sensors because we had someone who used to work for OneWire, and who helped actually invest a lot of money into the project. And the trouble with these sensors, and a lot of professors at the University of Cincinnati mentioned this when we were talking about this, there's an entire field on sensor fouling. So a lot of these sensors, when you see these large weather stations that have like the wind vanes on them and the rain meters, these things are usually pretty huge, and they're usually very expensive. They're 20 to 50 grand. The kind in the Arctic can run more than that because they need to withstand, bears attacking them. And Andrew worked on Arctic sensors where they had these huge stations that were doing just that. So these sensors, the water sensors were coated with the temperature sensors were coated with glass on one side. We had problems with the water measurement sensors where they were just reading, we would see like 11 gigaliters of gallon in a day, which was completely wrong. We found kind of fluctuations and problems with grounding. Eventually we got the site working really well. It worked fine for over a year, and we still have all that data, but I think a lot of the sensors are probably bad by now. And so there are ways to actually measure stormwater running through a pipe. So sewage stormwater, we found the company that was doing this. They had an acoustic sensor that they would mount in a sewer grate, and these were really expensive. I think they're either 5 or 10 grand each, and they had to be cleaned. You had to actually pull them out, and they were dishwasher safe. There were instructions on putting them in dishwashers, putting them back in. So having long-running sensors in these types of environment is very difficult. So that site, we have all the data from then, but I think right now all the sensors have actually gone out of use and are in disarray. But there is talk about getting that started back up.
How do you install your sensors in this pipe?
Those sensors, I wasn't involved on the installation phase. Quinn, our site manager, did most of that. So in the sewer grates, so we had pipes running out to the sensors, and we had just had PVC pipe, and they had seals on either side to keep them airtight. And then at the end, there's small little kind of holes on this. So imagine if there's a pavement surface, there's a grate on top. You could actually unscrew the top and reach down and reach the sensors for the temperature sensors. And then for the water sensors, they went down into the manhole. There were these thick gauge wires, and they're hooked up. So the tipping sensor was just hooked up to a magnetic reed switch. So every time the magnet went up and down, it would trip the switch and cause the counter to go up. And so those were all embedded down in the manhole. But those sensors were off to the side in the pump. So at least that was kind of sealed off in the pump by itself to keep it from getting too much damage. And so the water would have to go through the pump. And the sensor was actually sealed off from the disk itself. So the disk and the sensor were separate as well.
What's the average lifetime of your sensor?
I'm not sure. Those lasted for the entire life of the project, which was over a year. I think I have over a year worth of sensor data. In the vSense project, if you actually clone vSense, there's a Postgres and a MySQL file containing all of the sensor data, and it's over a year's worth of data. So those lasted quite a while. I'm not sure what the condition of those sensors are right now, or which ones are still active or not.
Can you summarize your perceived advantages for using Scala in this project rather than Java? What's the key advantages?
The key advantages I saw using Scala, it was a lot less code. You don't have all these getters and setters. You have things like actual properties. There was the code seemed a lot cleaner, and with the way that return values worked, especially when you look at the actions, everything seemed more laid out. It seemed more condensed, and you could kind of see straight patterns on where each path would take. I found the code just to be a lot more condensed and concise. There were a lot of problems using Scala. There are some things, especially when you find examples online where you see these pieces of code, you make these pieces of code work, and they're very small, but they're also kind of confusing because of the way that traits and mixins work and the way that the closures work around each other. Some of those things are hard to get your head around, but in general, I've found Scala to be a lot easier to work with Java, and just the speed at the ability to code these things seemed a lot faster than using traditional Java frameworks.
Did you find the compile time slow?
Not too bad. Yeah, the Scala compiler, back when we started, it was still on 2.8 or 2.9, and it does take quite a while to compile. But once you use build tools like SBT and only compile what you need to, it's really not too bad. And once I stopped actually deploying to a Tomcat server, once I embedded Tomcat in Jetty, the speed up went up quite a bit.
Did you have any incompatibilities with any Java libraries? Was Scala intrusive in any way, like the way it had some sort of types or anything like that, some Scalaisms that made it hard to work with Java?
It wasn't too bad. There are a bunch of Scala Java conversion tools to convert the collections, things like maps and things back and forth. Those worked pretty well. It's very easy to use Java code in Scala. If you need to use Scala code in Java, that can get very difficult, especially with some of the way that the collections and maps and options work. You can get these long strings of, it looks like 5 or 6 generics put together that don't quite make a lot of sense. And going the other way is actually pretty difficult. We had someone who wanted to write some analysis data on the images we collected, and I tried to provide him a Java API, and then I realized some of these things were actually going to be pretty difficult, and I had to work around getting the objects back into a Java form that he could work with.
Do much debugging on the Scala code?
Too much debugging. So I depended a whole lot on the aspect-oriented programming to give me that trace logging. So the trace logging helps a whole lot because I can see all the individual steps and components, every function that you go in and out of. But as far as debugging within Scala, it didn't seem that much worse than Java, really. I think some of the most troublesome parts were when you have these different types of type closures and the interesting collection types and wrapping your head around how some of those wrap and unwrap.
Big projects that are using BigSense? I mean, you said it's an open source framework. Is there any other?
Not yet. So that's what I'm hoping to work on. So there are a lot of things that need to happen to BigSense to get it more in general use. I want to get it to support WaterML2, which is a pretty big standard. And that way, once it supports WaterML2, we can start pulling stuff into QGIS. QGIS, it used to be called Quantum GIS, is the big open source GIS tool now. ArcGIS is a commercial tool that most geographers and GIS people use. It's really expensive. It's 20 grand for a one processor license. We got a copy for free at the university. It's a pain to set up, and I really want to start using it with QGIS and with other WaterML-based tools so that we can start using with other tools. I want to get LtSense eventually working with Data Turbine as well so that we can interchange those components as well. Cool. If you want more information, you can go to BigSense.io. We have a whole wiki. And if you guys aren't doing anything on the 12th, on the 12th, I will be at Fairy Duke for Voices in the Attic, which is a spoken word piece. I'll be the feature poet that night, and it will be pretty cool, and you can come watch me do other types of entertainment. But thank you.